Hey, welcome back to Math with Patrick and Quill. Today is December 13th, and we're solving problem 347 from the Daily Epsilon calendar. And the answer today should be 13 because that's today's date. We have some kind of exponential equation here, and once we find our value for x, we should round it up, and that should get us positive 13 for today. All right, so just looking at the problem as is, I do notice that eventually when x gets big, the left side will be greater than the right side. That's just because this term on the left will be super, super big after exponentiation, and big enough that even after subtracting a chunk from it, we are going to be larger on the left side than on the right side. Now, when x is small, however, the opposite is true. We could see this by, say, plugging in x equals 1 just to test something out. 729 to the power of 1 is just 729. Same thing with 702 and 676. As we can see, these are not equal to each other. And in fact, 676 is much greater than 27. So for the time being, when x is small, the right side is going to be larger. And knowing what the answer is for today, we could be pretty sure that when x is 12, we're also going to have the right side be greater. But then once we finally plug in x equals 13, we'll have the left side be greater. It's just that I don't want to do any of this because I don't really want to compute 729 to the power of 13. That's a really large number. Instead, what I think we could try to do is actually solve for the exact value of x. Normally, it's not really possible. Usually, when we have differences of exponent expressions, it's really hard to actually use the variable x and manipulate it. But we do have some common factors within these three numbers that makes it possible for today. 729 is a power of 3. This is 3 to the power of 6. I think what I'll do is I'll call it, well, let's write out all the 3's for a sec. I think what I'm going to do is call it 27 squared to then the power of x. So I can rename this as 27 to the power of 2x. And there's a reason for this because I'm noticing that there are a lot of 26s and 27s in this problem. Like 702. 702 is 26 times 27. So let's just call it that. Maybe 27 times 26, just to have it in descending order. That's still to the power of x. Maybe let's distribute that power of x right there. And on the right side, 676 is 26 squared. So we do get 26 to the power of 2x. And here, let's do a little bit of substitution. Let's just call 27 to the power of x, say, a, and then 26 to the power of x, b. And then here we could rewrite this as a squared minus ab equals b squared. And this kind of looks like a quadratic, so we could set it equal to 0. And that should be a minus b squared. And let's get this looking a little bit more like a quadratic. If I divide everything by b squared, I think I'll be able to get it to look more like a quadratic. And I know that I can actually divide by b squared. It is allowed because b should always be positive. Any number to the power of x, any other number, is always going to be non-zero and positive, actually. Just non-zero is the important part. I am allowed to divide everything by b squared here. We're going to get a over b squared, and then minus a over b minus 1 equals 0. And if I wanted to get this to look a little bit more like a quadratic, how about let's replace a over b with another variable c. C squared minus c minus 1 equals 0. Great, so we have a quadratic out of this as long as we follow our substitutions back up later. I think if we start solving for c, we're going to get valuable information about a and b, and then we'll just kind of see what happens from there. I believe this is a golden ratio quadratic. Just to be sure, let's maybe just quadratic formula this. So c equals negative b. b is our middle coefficient here. It's negative 1, so negative 1 is positive 1. Anyways, negative b plus or minus the square root of b squared minus 4ac all over 2a, and then a is our coefficient there. It's a 1, so 2 times 1 is just 2. we can simplify the radicand here. We have 1 minus -4, so that's 5. Dividing by 2, we get c. And c could be, looks like two different numbers because we have this plus and minus sign. Although I think I could throw out one of these. I know that the square root of 5 is greater than 1, so overall this is a negative number. And I think I can throw it out. Let's check back what c is going to be. C is a over b. There we go. So c is equal to 27 to the power of x over 26 to the power of x. Let's combine it like this, so we just have that ratio to the power of x. Anything to an exponent is going to be greater than 0, and so c has to be a positive number. So that does let me throw out this potential solution here. All right. And so I did say that c is equal to now 1 plus root 5 over 2. This happens to be the golden ratio. And there we go. We could plug it back into this equation here. We could say that 27 over 26 to the power of x is equal to the golden ratio of phi. I'll just write it all the way out, though. 1 plus root 5 over 2. And now all we need to do is just hit it with a logarithm, and we basically have our exact value for x. It's a little strange, but I could rewrite this as log base 27 over 26 of 1 plus root 5 over 2 is equal to x. This is just like the logarithm definition of rewriting exponential equations. Now that's a little bit weird, so I guess I could use some log rules to rearrange stuff. I mean, I don't really need to, but why not? First, I'm going to use the change of base rule, so I could have log of 1 plus root 5 over 2, and then log of 27 over 26. I mean, all of this is kind of unnecessary in the end. I'm just kind of renaming what this number is. We could use another log rule and split our fractions. So we get log 27 minus log 26. I could do that to the top two. So I'd get log 1 plus root 5 minus log of 2. And this is our answer. Or we could have typed it in like this. It's just, to me, a little bit strange to have a fractional base with a logarithm, but I guess that's totally allowed. Anyways, this doesn't really help me though, because I can't compute this in my head. And that's why we have calculators. So convenient. Anyways, log base 27 over 26. Actually, let me try that again. Log base, there we go, 27 over 26 of 1 plus root 5 over 2. We're getting, great, a number between 12 and 13, which if we do the ceiling function on it, this basically just rounds stuff up. Great, we get 13. So this 13 right here is our answer for today. Yay. I also wanted to show like the other forms that I wrote this in, right? I had like log of 1 plus root 5 minus log of 2. And then something kind of interesting about the change of base rule is that this logarithm could have any base, right? We could even do base, I don't know, pi, just for kicks, just to show that this base could have been really anything. Log base pi of 27. Let me get that 27 in the right spot. There we go. And then minus log base pi of 26. We get the same number. There it is. So 12 is too small, 13 is too big, and our actual answer for x is roughly 12 and 3/4, but then rounding it up, we get 13 for today. Just because I'm curious, I also want to know what 729 to the power of 12, okay, gosh, that's so big, minus 702 to the power of 12 is. And then I want to compare that to 676 to the power of 12. And so they have relatively the same size because I'm looking at this 10 to the power of 33. But the 9.1 brings this just a little bit greater than the 8.2. And then when I make all these exponents 13, hopefully the top number is now greater than the bottom. They do again have the same rough relative size, but then we can see that 6.3 is greater than 6.1. Cool. So that also shows that once we flip our x from 12 to 13, we switch which side is greater. And so we should find some value between the two, which is this one right here, or that one, which helps us get them equal to each other. And that is the whole answer. Hope you enjoyed. I'll see you tomorrow. Bye.